Can you hear me and also see the slide?
Yes, we see it clearly, Prof.
All right, great. So yeah, again, thank you for the very kind introduction. I will probably make one quick correction to the introduction, which is that I actually I have moved to Seoul National University last year. So it's been almost 2 years since I've moved. So I was in KAIST for 14 years, but now in a new university. So today I'm going to talk about some synthesis predictions for molecules and materials. I slightly changed the title, although I'll still cover large language models for inorganic synthesis, but I thought I would also talk about some organic synthesis as well at the end of the talk. So to give you some motivation, the ultimate goals of chemical science is really to discover novel compounds with desired properties. And those could be some molecules like antibiotic molecules shown on the left, or they could also be some inorganic solid state compounds like battery application, anode materials, cathode material, for example, as shown here. And in achieving this goal, informatics is really about using data to understand the structure and property relationships of the compounds. And by having that relationship, one would like to predict the properties of the compound given the structure, or you define the properties you want to achieve first, and then trying to come up with a structure using some kind of algorithms. And then the third aspect is the synthesis. I'm a computational chemist, and as a computational chemist, we all know that many of those compounds that we design computationally are not synthesized, and they are discarded in the laboratory. And so it would be good to have a model that can predict the synthesizability of those new compounds, or if they are synthesizable, synthesis recipes in more detail. So among these three aspects of chemical informatics, today I'm going to particularly focus on this last part, the synthesis aspect of the informatics. So with that, to give you sort of a motivation why we got really interested in this synthesis aspect, I'm gonna briefly touch upon some of the work on the generative models. We all know what generative models are. GPTs and other large language models are all generative models. And what we really want to do in generative models is to learn the distribution of the data. And once you have the distribution, then you can actually sample the data points. And for example, you can learn the distribution of portraits. And then by the learning, you can sample new data points. And you have this new portrait. And as a chemist, you try to learn the distribution of the compound in the compound space. And try to design new compound with the desired property. And we were one of the very first groups who used generative models to generate new inorganic solid state compounds. And we have used variational autoencoder and GAN, and we found several compounds with new space groups and so on. And we tried to synthesize them in collaboration with experimentalist John Gregor at Caltech. Well, we couldn't synthesize them. And so that was the point when we realized that design is one thing, but synthesis is another. And actually, because it's the synthesis that we want to realize that at the end of the day, we should really have a model that can predict the synthesis ahead of experiments. And that way we can save the time and the cost for the new discovery. So that was the motivation. And so that was about 2017, 2018. And then we started to work on the synthesis prediction since then. So for these synthesis predictions for inorganic compounds, the task that we are trying to address is essentially classification. So you have a compound in as an input, and the model is designed to predict whether the compound is synthesizable or not. So it's basically binary classification. Except that it is not the usual binary classification because in the conventional positive negative classification, you have the positive data and negative data, and the model will predict for an unknown example whether it is positive or negative. But for synthesis, if it has been synthesized, it's a positive data. But if it has not been synthesized, that doesn't mean that it's not synthesizable. It simply means that it has not been synthesized yet. So it's not a conventional positive and negative learning, but it's basically positive and unlabeled learning. And in short, we call it PU learning. And so we've done that. And we've used Motu's project database, which consists of about 50,000 positive data and about 80,000 unlabeled data that are really obtained by the elemental substitution of the existing synthesized compounds. So we've done this PU learning for this inorganic compound database, and our model has about 87% recall accuracy, meaning that 87% of the time we will predict the synthesized compound as synthesizable. To cross-validate the model, we did some time split benchmark where you excluded the compounds that have been synthesized after 2015. So you only train the model up to the database of up to year 2015 and test the model trained that way against those compounds that have been excluded intentionally, namely the compounds that have been synthesized between year 2015 and 2020. And our model, again, has about 80% recall accuracy, consistent recall accuracy. So that validates the validity of our model. And one thing that we found interesting was shown on the lower left, where we compare thermodynamics and synthesizability scores. As a computational chemist, because the synthesizability really is not a well-definable quantity because it could mean many different things. So we normally compute energy of a whole or some kind of formation energy like energy estimations. And but when we compare that, we find that even if the compounds are thermodynamically very stable, they may have low synthesizability scores. So synthesizability scores and thermodynamic metrics do not go always as parallel, although they are related in one way or the other. And on the lower right corner, I am showing you the application of this synthesizability machine learning model towards a few hypothetical database, MP virtual, OQMD virtual, and you see that about 10 to 20% of them are predicted to be synthesizable. And that means that for these hypothetical inorganic compound database, the remaining 80 to 90% of them may be hard to synthesize, even though some of them may be recognized as having promising properties. So having this kind of filter in your screening pipeline, one might be able to save some time and cost for experimental attempts. Now you can apply this to a particular class of materials. In this case, we applied it to perovskites. And for perovskite synthesizability, there is a heuristic rule called Goldschmidt rule. And Goldschmidt rule basically estimates the synthesizability of perovskite, where the composition is stoichiometry is basically AbO3, and Goldschmidt rule predicts the synthesizability of this compound based on the ionic radii of A and B, relative ionic radii. And here on the upper right triangle, you see that green dots, and green dots mean that they are predicted to be synthesizable according to Goldschmidt rule. And the dark greens mean that they have been actually synthesized. And so you can see that there are many light greens. They do not overlap with the dark greens, meaning that they may be false positives. On the other hand, machine learning models, you can see that they are more selective in predicting the synthesizability of these stoichiometries. Now you can extend the model and try to build a model to predict the synthesizability based on the stoichiometry, the compositions. And because you can predict the synthesizability of these compositions for an arbitrary ratio of X, Y, and Z, you can actually draw a synthesizability map. And here I'm showing you the synthesizability map of barium, vanadium, and oxide ternary compounds. And on the left-hand side, you see that the stars are the ones that have been already synthesized. And the blue regions are high score regions, meaning that they are highly synthesizable. And you can see that all those compounds that have been already synthesized fall into this blue region, highly synthesizable region. I should mention that this model was trained without this ternary compounds database. So it's not like the model has memorized the synthesizability of these compounds. They have learned the synthesizability of these ternary compounds based on other inorganic compounds. Okay, now we have a synthesizability prediction model. Can we go beyond the synthesizability and predict synthesis recipes, the precursors of the crystal synthesis? And there are several other synthesis recipe prediction models for inorganic crystal compounds in the literature, and many of them are based on generative models. But those generative models can actually sometimes, quite oftentimes, yield very unrealistic compounds. And so instead, we formulated this inorganic retrosynthesis as template-based approach. And that was motivated by the fact that if you look at the inorganic synthesis database, then unlike organic synthesis, where you can choose reactants from millions of different kinds of organic compound list, but for an inorganic synthesis, oftentimes people use the same precursors over and over again. And so if you look at this database curated by the Cedar Group, then there are about 100 or of the order of 100 precursors that are often used. And so instead of the model predicting the precursors randomly, we sort of have a predefined list of precursors, like 50 to 100 of them. And the model is trained to select the correct set of precursors from the list. And we call that as a template-based approach. And then you do some probabilistic modeling using some kind of graph convolutions. So the target is the synthesis of target compound shown on the left in this table. And in the middle, you have the precursor sets that are predicted to be correct. You can also take some statistical accuracy. And for example, top 5 accuracy means that if you make 5 predictions, then what are the chances that the ground truth answer is within that 5 predictions? And we get about 96% of top 5 accuracy. Okay, so those are the sort of inorganic synthesis predictions that we've worked on using these kinds of mostly graph convolutions and those models. Now, LLMs are now increasingly used in different disciplines in chemical science. For example, MOF, data extraction, molecular property prediction, organic synthesis planning. But for us, we were wondering whether LLMs can address inorganic synthesis problems also. And so this basic pipeline is that you can try this pre-trained, already available off-the-shelf LLM and for synthesis predictions. And if it doesn't work as much as you want, then you can actually fine-tune the model and then see what happens. So we applied the LLM for 2 tasks. One is synthesizability, 2 precursor selection. So the 2 tasks that I already explained to you are the target sort of task for LLMs. So it's all text-based. So all you need is a text description. And so this is sort of the example user prompt is the following. You are an expert inorganic chemist. Determine if the following compound is likely to be synthesizable based on its composition, answering only P and U, and you write down the inorganic stoichiometry. And then in this fine-tuning process, you show the model examples of synthesized compound and examples of unlabeled compounds. And by showing machine these kinds of examples, you can actually fine-tune the model. And you can do the same thing for synthesis recipe predictions. And we now compare the results with the results based on these customized bespoke models that I talked to you earlier, namely these models. I talked about this inorganic synthesizability model and synthesis recipe predictions. So we compare our results with those 2 models. The first one, we call it STOI-CGNF, and the second one, we call it Allen-Weiss retro. Here's the result. So STOI-CGNF is the result from our customized model, graph-based model I talked about earlier, and GPT 3.5. FT is GPT 3.5 fine-tuned. You can see that those 2 results are very comparable, very similar. So for synthesizability predictions, x-axis is again the probability between 0 and 1. 0 means unsynthesizable, 1 means synthesizable, and somewhere in between, meaning some probabilistic synthesizability. And down below, you have this synthesis recipe prediction results. And again, GPT 3.5 fine-tuned. And Allen-Weiss, it means that it is the bespoke model that I talked to you earlier that is based on template definitions for the precursor selection. And again, you see that this Allen-Weiss predictions and GPT 3.5 fine-tuned are pretty comparable. And we were quite surprised to see both of these results because GPT fine-tuning is very simple. All you need is some text prompts and fine-tuning. It doesn't cost much. It costs about less than $50 for fine-tuning process. And so based on these results, without that, maybe in the future, these kinds of fine-tuning of LLMs should be used as a very strong baseline for any models that you develop. So of course, it'll make our jobs harder, but there's no reason not to try these kinds of LLM fine-tuning for the task that you're interested in, and they should be probably used as a strong baseline in the future. Now, so these synthesizability and synthesis recipes are both based on stoichiometry for the compounds. But at the end of the day, when you synthesize a particular compound, you really mean not the composition, but structure, right? For example, if Mn3O4 is predicted to be synthesizable with high score 0.862, close to 1, what structure do we really mean, right? Because there could be multiple different polymorphs with the same stoichiometry. But if you actually run these kinds of synthesizability prediction for a particular structure that I showed earlier, then they have very different scores. So then the question is, can LLM also predict the synthesizability of these crystal structure-specific cases? So to do that, you need to convert the crystal structure in XYZ Cartesian coordinates into some text. And so for that, we've used a RoboCrystallographer. And here's an example of the text description of a particular inorganic structure. And you see that this text description contains some space group symmetry and some bond lengths and local coordination environments and so on. Here's the result. So there are several different models. So let's only focus on here blue and green first. Blue is PU learning model, crystal graph convolutional neural net. So this blue bar is the one that I showed you earlier, based on PU learning. And green is the same PU learning, but the input is not convolutional neural net for graphs, but it's actually text embedding generated by GPT. And you see that the same PU learning, but with the GPT text embedding, actually has a better performance. And so it means that for these kinds of classification task, this kind of text embedding, which has space groups and local coordination environments, they actually represent the crystal structure better than the graph representation of the crystal structures. And then the gray is the final model, which is the GPT model fine-tuned, and that has the highest accuracy, although the accuracy more or less or pretty comparable. And one thing that I wanted to also highlight was this comparison between thermodynamics and synthesizability metrics. Again, so on the right, you have this about 12 compounds that were screened thermodynamically by Toyota Research Institute. They use these thermodynamic sort of estimations and to identify some synthesizable compounds so that they can try experimentally. And you can see that all of these compounds has energy above all zeros or very close to the zeros, meaning that they are thermodynamically basically stable. And they try to synthesize all of them, and none of them have been synthesized. So they failed to synthesize all of them, although they were predicted to be synthesizable according to thermodynamics. Now, if you plot that according to LLM score measure, then you see that you see this vertical red line, and all of these 12 compounds are on the left-hand side of this decision boundary, meaning that they are all predicted to be unsynthesizable based on this model. I'm not trying to say that this synthesizability metric, synthesizability, the score, are better metric than thermodynamics. I'm just trying to say that this conventionally used energy-based estimation cannot alone explain the synthesizability of the compounds. And it should really be sort of the complementary use of this thermodynamics and this kind of synthesizability classification model. So they are really complementary. Okay, so that's about the inorganic synthesis aspect that I want to talk about. And I'm going to spend the remaining maybe 5 minutes or so to talk about organic synthesis. For organic synthesis, you have reactants on the left-hand side, you have a product on the right-hand side, and there are two tasks. So the first one, you want to you define the target compound, and then try to predict the reactants, and that's called retrosynthesis. Or you can start with a set of reactant molecules and try to predict the product. So it's basically trying to predict the reactivity of your reacting molecules. Now, for these kinds of forward prediction or retrosynthesis, the most popular model as of now is actually a language model, which is called a transformer. In this case, you represent your molecules, your reactants, as some kind of smiles string. So it's like a sentence. Now you also represent your target compound also as a smiles string. And then you look at this chemical reaction as a process of translation from one language of reactant to another language of product. And so hence you can use this transformer architecture for the prediction. And then you can do the same thing for the retrosynthesis. So it has very high accuracy, but it's not explainable because you don't know, like chemical intuitions, why certain reactions occur and why certain reactions do not occur. Another way of predicting this reaction is template-based. If your task is the retrosynthesis, and if you're given a target compound, organic chemists would see the compound and try to see which bond to cut. So in this case, CM bond to cut, and then what functional groups to add after cutting the bond. So that might be the way that organic chemists look at the reaction and predict the reaction. So you can mimic that in machine learning model also. So basically, you try to predict which bond to cut and which functional groups to add, or which rules to apply, or which templates to apply. And so that's called a template-based model. And there are other template-based models, but I'm just talking about our model just for the sake of time. We obtain about 86% top 5 accuracy for retrosynthesis and 96% top 5 accuracy for forward synthesis. And these two accuracies are one of the state-of-the-art models as of now. Now, how do they compare with synthetic chemists? So we asked the reaction outcome of 80 reactions to 11 human experts. And this experiment was designed by a colleague. It's a small scale benchmark. And best human expert, according to Holly's paper, got about 61 out of 80 correct. And molecular transformer got about 70 out of 80. And our model, we called it a local transform, this template-based model, got about 75 out of 80. We're not trying to say that these AI models can beat heatback to human expert, because it's very small scale. And so by all purposes, it should only be taken as qualitative measure. But nonetheless, it does suggest that these data-driven synthesis predictions can actually make very reasonable predictions. So that's the status. Now the bigger question then is, can AI model discover new type of chemical reactions? Many people in the field may say that may be difficult because all existing models predict the reactions based on the reactants product information only. Although synthetic chemists actually look at electron rearrangements and they stick to the mechanisms. And by that, they can develop new reactions. Then what hampers us from following the same chemical intuitions, looking at mechanisms and predicting the reactions based on mechanisms? The current bottleneck is that there is no large-scale reaction database. There are several large-scale reaction database, but they only have reactants and product information, no mechanistic database. So the first step to achieve mechanism-based reaction prediction should be the generation of large-scale mechanistic data. And that should be done in two steps. First step is the automatic atom-to-atom mapping. Atom-to-atom mapping means that you basically identify a particular atom in the product came from which atom in the reactant. And so that's called atom-to-atom mapping. And once you have that, then you can do this mechanistic labeling. But because you want to scale it up in a larger scale, you cannot do it one by one by hand. So you need to automate the process. So for the sake of time, and we've done that. I'll just skip. And then this is sort of the mechanism that was generated by our two models, this atom mapping model and automatic reaction mechanism generation model. And so for a given organic reaction, this model can generate these arrow pushing diagrams, which indicate the movements of electrons from one region to another. Now with that, we finally recently built a model which now can predict the reactions based on the mechanisms. And with that, we were able to screen 3 million chemical reactions, virtual chemical reactions, and try to find new type of reactions. We found that out of 3 million reactions, 77% of them show that they are not reactive. And about 15% are known transformations, already known reaction types. And we found that about 7 to 8% could be new reaction. So we are in the process of analyzing these new reactions, but it shows some promising results. Okay, so my time is already done. So people talk about structure property relationships, but we also do that. But today I focused on structure and synthesis relationships, right? And talk about synthesizability and synthesis recipes. And if you think about it, all these reaction prediction models are not that long. They all been developed in only recent years. So there are many opportunities ahead. For example, interpretable synthesis foundation models, synthesis condition predictions, yield predictions, and finally these chemist-like mechanism-based predictions are really the way to go. So here are my brilliant students of mine who did all the work, and excellent collaborators, Alan, John, Aaron, Joshua, and Professor Seung-Gi Han. And thank you for your attention.
Thank you very much, Professor Yousung, I think for this very engaging and informative presentation. And we have seen clearly that your insights into using AI and chemistry has been incredibly valuable in a way that you showed the reality and and you came across different points and pinpoints that exist within this area. And we really truly appreciate your contribution to today's webinar. And I would like to thank you a lot for the very nice presentation that you presented today. So we'll leave the floor in case anyone has any questions. We can see some questions in the Q&A, and I don't know if we can take 2 from your valuable time, Professor.
Yeah, so the first question is, how can AI and machine learning models predict chemical reaction without direct information about the energy of molecules? So what we do is really, again, I mean, all these AI models and machine learning models, they do pattern recognitions, right? So depending on how you represent the reaction, how you represent the molecules, you can represent them as smiles, as these transform-based models do. And then they really learn how these particular smile strings convert from reactant to product. And by showing AI models a million of such examples, the model actually captures some essence about reactivity. And based on the chemical environment, this and this will be converted to an other sort of smiles string. And so that's how these models actually predict the reactions without the information about energetics. So that I hope that answers the question. And then the second question is, any open source published for your work? Yes, all of this work, we put the open source code on the web in the GitHub. So you can read our papers, and there is a link, so you can try that.
All right. Thank you again, Professor Yousung, for this very insightful presentation. And we appreciate the efforts and dedication put together into this. So thank you a lot. Okay, so now we are really excited to move to one of our scheduled speakers, that Christoph Volker, in which he was not basically be able to join us live today due to some travel constraints and given the delay that we had in the morning. So, however, we are pleased to share his pre-recorded video prepared by himself. And just like to introduce the next speaker, I'll just go over his bio. So Christoph Volke is a research scientist at the Federal Institute for Materials Research and Testing, BAM, in Germany. And he's focused on accelerating experimental material science through data-driven approaches with a huge background in engineering and understanding complex systems, where he basically seeks to optimize material properties using machine learning and semantic databases. And this is aiming to reduce greenhouse gas emissions from cement productions, as we have seen multiple tools that he is already presenting. So today he wanted actually to present this SLAMD, which is called the Sequential Learning App for Materials Discovery. And we will be starting the video after this talk. So.
Hi, and welcome to this video. Today I'm excited to introduce our newest addition to SLAM, the Design Assistant. In this quick tutorial, I start with some background information and then give you a hands-on demo to show you how this tool can help you in the lab. Our mission has always been to accelerate sustainable material development by providing easy-to-use and cutting-edge AI tools for lab workers and researchers who are pushing the boundaries of green materials. With the Design Assistant, achieving this mission has become even easier. The Design Assistant offers 2 options. First, it simplifies the creation of new SLAM projects. If you prefer using SLAM the traditional way, there's a link in the description to a tutorial. To get started, the Design Assistant guides you through the initial steps and ensures you provide all the required inputs. Additionally, we have something exciting and new: the LLM-powered zero-shot Design Assistant. Here's the thing. Sustainable materials can be extremely complex. The challenge is that innovation requires extensive knowledge, and the pace of knowledge creation is incredibly fast. New resource streams are constantly being investigated, and thousands of papers are published every month, making it hard to keep up. It often takes a scientific career to become a true expert in a material. Meanwhile, practitioners need solutions today. This is where LLMs offer a clever and innovative solution. Trained on a web-scale dataset, LLMs include deep domain expertise that was previously hidden in scientific institutions, but is now accessible to everyone. So how does this work? LLMs are exceptionally good at extracting and storing concepts from the text they're trained on. These concepts are stored in the inner representation, known as the hidden states. You can easily access concepts and knowledge embedded in the LLMs through prompting. This allows you to tap into the widely reported good practices, but also to combine concepts and latent relationships in the field flexibly. Think of a new material that belongs to a non-material class. All relevant knowledge can automatically be transferred to it. For instance, introducing industrial waste streams with geopolymer means that existing knowledge about geopolymers can be applied. Additionally, LLMs can provide information in any format, making it easier to transform complex scientific concepts into actionable formulations that you can implement right away in the lab. So, what makes a good prompt? To access all this knowledge, the design assistant guides you through a structured process, ensuring your prompt includes all the necessary elements of your design tasks, such as the constituents, the powders, liquids, processes, and more. It also covers information about your design target, whether it's strength, cost optimization, eco-footprint, or other factors. Additionally, relevant concepts that apply to your material should be included. You might ask, didn't you just say concepts are stored in the LLM? So we actually wrote a paper on this, benchmarking LLMs in concrete design tasks. It turns out that although these concepts are in the hidden layers of the LLM, performance improves significantly, especially in the beginning, if you add relevant design context or knowledge to your prompt. By showing the LLM what it already knows, you ensure the LLM activates the relevant concepts from its hidden states, giving you the best answers. But don't worry, based on your previous inputs, the design assistant creates the relevant knowledge automatically. Additionally, you can add crucial context such as, please consider simple solutions, or we already tried increasing the concentration. What more can we do? This includes boundary conditions and other specific details to refine the response further. Okay, so let's try out the Design Assistant zero-shot design capabilities. And I want to use a case study we've recently published. Although the Design Assistant was not available at the time, I want to showcase how it could have helped us and saved time when we were faced with this design task described in the study. So hopefully this tutorial will give you a practical understanding of how to leverage the tool effectively from the very beginning. So what was this about? In this study, we were aiming to develop a geopolymer binder formulation that exceeded the 100 megapascal strength after 7 days. So we wanted to maximize the compressive strength of this material. We did this in 8 consecutive rounds where we collected data and trained a machine learning model to improve the suggestions in the next round and find a good material after some time. And as you can see, we were successful, especially at the end. We were able to find multiple formulations that exceeded our threshold. So the design assistant would come in here at the very beginning, where we didn't have any training data and made a rather poor choice in the initial data set. So the question is, if we would have collected better data, would we have ended up with these high performance materials much, much quicker? And the design task specifically was based on a powder from glass waste residues. And we wanted to design an activator liquid with a complex composition where some of the compounds were substituted with cheaper byproducts from industry. And the objective in the initial round was to collect training data, which means the data should cover some of the variability within our design space. So let's get started. To get to the Design Assistant, just visit the SLAMmed homepage and click on this top menu on Design Assistant, or open the side menu and click on Design Assistant. And you'll be met with our brand new assistant. On the top, you'll find some infos on the usage. And down here, the assistant greets you and tells you all about the functionality. So let's get right to the zero-shot designs using large language models just selected. And in the next step, the Design Assistant explains the process to you. And basically now we go step by step through the design problem. Start with which material we want to design a binder. Let's add the target property. We could add a custom property or choose one from this list. In this case, we want to maximize the compressive strength. So let's just use this preset and enter desired strength. In this case, we want to reach a target strength of 100 megapascal. Submit that. Now let's select our powders. In this case, we're going to use geopolymer. And the liquid, I'm going to use an activator liquid. Anything else? No, thank you. We're just using this basic setup. And now we have the opportunity to enter background information on our design problem. And I've prepared a little text here, which summarizes the design problem, basically laying out the background. We have a powder made from glass residuals, glass production residuals, and fixing materials, the composition of the powder, the objective. We want to collect training data, so please increase variability in your suggestions, your task, find 4 suitable high performance materials on this grid. Okay, we can enter this, we can explain in natural language what we expect from the Design Assistant. At the bottom also the output format, so we want it in this way. So let's just submit this, and now we come to the part where we can create, with the click of a button, the general design knowledge for this specific task. So this text now comes from GPT-4o, and it starts with some disclaimer. We can edit this text, right? It starts with some disclaimer and then some concrete design rules for this material and this design target. We can verify them, we can check them, we can add it. We could, for instance, delete this text at the beginning and at the end, because it does not really add any specific content. And then just click on Generate Formulations. And we should receive 4 formulations with high variability and good performance for our geopolymer design problem here. Let's see. Okay, we get 1, 2, 3, 4 different formulations. The variability appears to be high. We have high sodium silicate content, which is probably the winning answer, and we have lower ones, and there's a lot of variability in the parameters. So just simple as that, we get a design grid to get started, and just by looking at it, knowing the outcomes of what we tested, it seems like this might actually already be a very good candidate. So I'm really glad we got this result. We can now save it. So now it's saved in the backend, and we can download the session, and then we have it locally uploaded the next time again. So what's new with the Design Assistant? Let's summarize. The Design Assistant now provides easy access to AI-driven materials design through natural language, which makes it much easier to get started. Additionally, no training data is required for zero-shot designs, allowing you to master new design problems right from the get-go and begin with high-performing materials tailored to your requirements. The Design Assistant guides you through a structured prompt generation process, ensuring you include all necessary elements for your design task. Important design knowledge relevant to your task is generated automatically to improve the output. Furthermore, natural language now allows you to incorporate fuzzy concepts, such as what's my intention, boundary conditions, and fuzzy design rules, into solving your design problem. This means you can seamlessly integrate high-level ideas and constraints into the design process. This makes it much more flexible and comprehensive. Follow this link to try out the Design Assistant today.
All right, so basically we're just like to thank Professor Christoph Walker for his basically very insightful video that is basically published also on YouTube. We appreciate the effort and the dedication.
Hallo und herzlich willkommen zum Abteilungsseminar mit dem Titel Towards Autonomous
So, basically, we appreciate the effort and dedication that's placed into sharing his experience with us, even though he was not be able actually to be here today with us. And so our next speaker will be Mona Shahrani. She will be presenting the Track 1 challenge to the participants, in which we look forward to that in 40 minutes. And we will have a break of 40 minutes, and then after that, we'll come back. So enjoy your break.